Welcome back, everyone. We are starting chapter 4 today, and chapter 4 is a big one. This is probability, and this is sort of a game changer, very different than the first 3 chapters. So we are going to be walking through this. Section 1 is just sort of an introduction, and then sections 2, 3, and 4 are a little bit more application. We have quite a few applications here. So as always, we have to start out with some definitions. Improbability and experiment is any process with uncertain results that can be repeated. Now, I want to really make a big deal out of that can be repeated. In science, if someone does an experiment, let's say in Australia, they do some amazing physics experiment and they get amazing results. What they do is they post exactly what they did and how they did it so other scientists can repeat it. And if other scientists can repeat it and get similar results or the same results, then there's a lot. That means that there's quite a bit of more data to support this idea. If something happens once and it can't be repeated, it's thrown out. It's considered a fluke. Something wasn't right. It couldn't work that way. So it's got to be repeatable. In the short term, results are uncertain, but in the long term, the proportion in which a certain outcome is observed can tell us quite accurately the probability of that outcome. That brings us to the law of large numbers. And basically, the more you do an experiment, the closer you're going to get to the true probability of what it is that we're looking at. For example, if I were to take a coin and flip it 10 times, and let's say I got 3 heads and the rest were tails, well, that would mean 30% of the time I was getting heads. But we know it should be 50%. And 30%, 50% are quite off. So what happens is if I were to do the experiment of flipping the coin 10 times, and I were to do that experiment 100,000 times, and then take the average of all that, I'm probably going to come really close to 50%. So the more you do something, the closer you're going to get to the true probability of that outcome. All right, we have a few definitions here. The sample space usually we use S of a probability experiment, is the collection of all possible outcomes. So for example, if I'm going to roll a die, that's a single dice, the only outcomes I can get is 1, 2, 3, 4, 5, and 6. That's it. There's nothing outside of that that I could possibly get. Next up, an event is any collection of outcomes from a probability experiment. Events may consist of one outcome or more than one outcome. And we often use E, F, G, and H and so on to represent these events. Typically, we write out what the event actually is. That way, we don't have to guess what E means or F means. And now we're getting to the interesting stuff. An unusual event is an event that has a low probability of occurring, typically less than 5%. It's not always 5%. But that's sort of the standard that we go to. And finally, a probability. Model lists the possible outcomes of a probability experiment and each outcome's probability. And here are some rules of probability. P of E represents the probability that event E occurs. So, for example, flipping a coin, it would be P of heads, maybe. P of E is always between 0 and 1 inclusive, meaning it could be a 0 probability and it could be a 1 probability, meaning 100%. If an event is impossible, then the probability is 0%. If an event is certainty, then the probability is 1 or 100%. And so let's interpret our statement here. The probability that an individual walks to work is 0.03. This means if we survey 100 individuals, we would expect about 3 to walk to work. All right. And we're going to learn about a tree diagram, using a tree diagram to describe the sample space and fundamental counting rule. If a basketball player shoots 3 free throws, describe the sample space of possible outcomes using S for a made free throw and F for a missed free throw, meaning S is success, F is a failure. And then what is the size of the sample space? So let's start out. The first shot is either a success or it's a failure. Second shot is either a success or it's a failure. The third shot is either a success or it's a failure. And I'm going to write out all the entire sample space. So S, 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 success, success, failure, success, failure, success, and success, failure, failure. Next up, fail, success, success, fail, success, fail, 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 success, and fail, fail, fail. Now our sample size here is a total of n equals 8. So this is the entire thing. If any basketball player shoots 3 free throws, these are the only possible outcomes. Not too bad. You have to get a little systematic when you're listing these out like this. So we're going to do another one here. If a person rolls a 4-sided die and then flips a coin, describe the sample space using 1, 2, 3, 4 for the die outcomes and HT for the coin outcomes, meaning heads or tails. And then what is the size of the sample space? So we'll do another tree diagram. So, oops, let's go back to black here. They can roll a 1, a 2, a 3, or a 4 with the 4-sided die. And then they flip a coin. It's either a heads or it's a tails. And let's write out the sample space again. 1 heads, tails, 2 heads, 2 tails, 3 heads, roll of 3, pardon me, and then a heads, roll of 3, and then a tails, roll of 4 and a heads, roll a 4 and a tails. And you can see once again, our sample space in this case is n equals 8. So we have 3 ways of determining a probability: empirical method, classical method, and subjective method. This is the bad one. And we'll mention that a little bit later. But typically we try to do the traditional. I'm not going to distinguish too much between the two because they're, in the end, they come out to be about the same thing. A number cube with faces labeled 1 through 6, that's a die, like a regular 6-sided die, will be rolled once. The number rolled will be recorded as the outcome. Give the sample space describing all possible outcomes, then give the outcomes for the event of rolling a number from 3 to 6. So let's see what the sample space is. Oops. This is going to be a 1, a 2, a 3, a 4, a 5, or a 6. That is the sample space. And the event from rolling a number from a 3 to a 6, well, that's going to be a 3, 4, 5, and 6. Now, yeah. And let's move on and actually find some probabilities. A survey of 500 randomly selected high school students determined that 288 played organized sports. What is the probability that a randomly selected high school student plays organized sports? So the probability plays sports. Well, my denominator is going to be the total. The total of 500 high school students. And it turned out that 288 of them played organized sports. Okay, so let's grab our calculator. 288 divided by 500. Oops. 576. So here is our probability or proportion. We could rewrite that as a percent. That's about 57.6%. So a little over half. And we know that 250 is half of 500. So 288 is going to be a little bit over 50%. So our answer makes sense. All right, probability involving one die choosing from n distinct objects. A box contains 10 cards, excuse me, labeled J, K, L, M, N, O, P, Q, and R, and S. One card will be randomly chosen. What is the probability of choosing a letter from N to Q? First of all, there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of an N to a Q is going to, first of all, be out of 10. And how many of them are from N to Q? Let's mark that up. N to Q. I'm seeing 1, 2, 3, 4. And we can reduce it. We don't need to reduce these unless it says to. But ALEKS will accept either. So both of these are correct answers. All right. In an aquarium, there are 6 large fish and 8 small fish. Half of the large fish are blue. One fish is selected at random. Find the probability that it is a large blue fish. Okay. So well, how many fish are there total? There's a total of 14. 6 large, 8 small. Now, how many of them are blue? Well, if we go to the large fish, it says half of the large fish are blue. There's 6 large fish. That means that there's going to be 3 large blue fish. And that is our answer. Not too bad. All right, we have a few more from ALEKS. A coin is tossed 3 times. An outcome is represented by a string of the sort HTT, meaning heads, then tails, then tails. The 8 outcomes are listed in the table below. Note that each outcome has the same probability. For each of the 3 events in the table, check the outcome that are contained in the event. Then check the last column and enter the probability of the event. All right, let's take a look at event A. A tail on both the first and last tosses. I'm seeing one here. I'm seeing one here. And I'm seeing, that's it. So what's the probability? That's going to be 2 out of the 8. And again, you could write 1/4 or 2/8. ALEKS accepts either. Event B, a tail on the last toss. Okay, we have here, 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 and here. That's going to be 4 out of the 8, or 1/2. Again, you could put either. Event C, a head on each of the last 2 tosses. A head on each of the last 2 tosses. That is going to be here, here. I think that's it. Yep. Again, that's 2 out of 8. All right. The state lottery board is examining the machine that randomly picks the lottery numbers. On each trial, the machine outputs a ball with one of the digits 0 through 9 on it. The ball is then replaced in the machine. The lottery board tested the machine for 25 trials and got the following results. So let's interpret what this means. A 0 came out 3 times out of the 25. A 1 came out 7 times. A 2 came out once. A 3 came out 0 times, and so on. Part A. From these results, compute the experimental probability of getting a 4. Well, there were 4 out of 25. Let's write that a little bit better. So the probability of getting a 4, there were 4 of them, happens to be the same number, out of the 25. Let's see what that gets us. 4 divided by 25, 0.16. Now, that means 16% of the time a 4 came out. Assuming that the machine is fair, compute the theoretical probability of getting a 4. Well, if it's fair, then it should be, this is probability of 4 again, but this is the theoretical now. The practical is part A, theoretical is part B. Out of the 10 ping pong balls, or whatever they are, it should happen once out of the 10 times. All right, so it looks like it was a little bit higher, but pretty close. Assuming that the machine, part C, assuming that the machine is fair, choose the statement below that is true. With a small number of trials, it's surprising when the experiment probability is much greater. No, it's not surprising at all. It's such a low number. With a small number of trials, it's not surprising when the experimental probability is much greater than the theoretical. That's definitely true. And you can imagine, instead of just doing 25 of these trials, we did 125,000 of these. But we're going to get a lot closer to 0.10 probably. And the last one, with a small number of balls, the experimental probability will always be much greater. That's not true. It could easily be much smaller or a little bit smaller. All right, so we have Venn diagrams now. All right. So we have C and D, and we have an intersection. So I'm going to write right here that this means and. So this is intersection. And what that means for us is that we are going to only shade in the part where there's overlap. That's what and means. It means it's got to be in C and D at the same time. Now this symbol here is going to represent or. This symbol's the union symbol. Union. And that's saying that it could be in C or D or both. Both are perfectly fine. Now, of course, when you're using ALEKS, you'll be able to have a better shade than my my pen here. All right, we're almost there. So we have another Venn diagram. A pet store surveyed 178 people to see how many own a dog and how many own a bird. The Venn diagram below shows the results. Each number gives the number of people who fall into the Venn diagram category. Okay. All right. So how many people own a bird? Okay. Everyone in that circle is going to own a bird. So that's going to be 39 plus 28. 39 plus 28. 67 on a bird. You, of course, don't need to write in the 39 plus 28. You just put in the 67. How many people own a bird or a dog or both? I think it says, or both. A bird or a dog or both. That's going to be 37 plus 39 plus 28. I'm getting a 104. Ooh, that 4 looks weird. How many people do not own both a dog and a bird? Pardon me. Okay, so as we're looking at this, the only thing that we need to not include in this case are the people that own both a dog and a bird. So that's going to be 37 plus 28 plus 74. 37 plus 28 plus 74. The 74 people don't own a dog or a bird, is what we would interpret that as. And I'm getting 139. All right, and a subjective probability is bad. This is when someone just kind of guesses. Well, I think 80% of the people agree with me. Where are you getting the 80% from? You're just making that up. So we try to avoid that as much as we can. All right, suppose a single card is drawn at random from an ordinary deck, and we'll talk about this sample space. It's come to my attention, a lot of people have never played cards before, which is shocking to me because I enjoy playing cards. The way standard deck of cards works is there are 4 suits. There are clubs, diamonds, hearts, and spades. The clubs are black cards. Spades are also black. Diamonds and hearts are considered red cards. In each suit, there are 13 cards. They are numbered 1 through 10. We don't call a 1, we call it an ace. And the last 3 cards are what are called face cards. We have a jack, a queen, and a king. That means that the total sample space is 4 times 13, or 52. That's going to be our denominator each time as we go through this. All right, so let's start at the beginning. Probability of a red queen. Well, how many red queens are there? There are 2. And they want us to express this as a reduced fraction. So there are 2 out of the 52, which reduces to 1 over 26. Part B. Probability it's a face card. All right, again, my denominator is going to be 52. And how many face cards are there? These are all considered face cards, all the way down. So that is 3 times 4. That is a total of 12 face cards. That reduces to 3 over 13. All right, next up, part C. Probability it's a diamond. How many diamonds are there? There are a total of 13. Yeah, so that's all of the diamonds. And that's going to reduce to 1/4. Or D, the 2 of clubs. 2 clubs. Well, there is exactly 1 2 of clubs. It is right there. That's it. That's the whole thing. And that does not reduce. That is our answer. E, probability that it's a black card. How many black cards are there? Well, there's 2 full suits. That's going to be 26 out of the 52, or half. Part F, my wife is from another country and she actually has a green card, so she thought it was cute to put this in. And in a standard deck of cards, there are no green cards. And that is section 4.1. I hope that you found it helpful.